Okay, so welcome back from the weekend, grade 11s and 12s. So we're going through our last lesson on kind of the math of chemistry, which we call quantitative chemistry. So then after this, we're going to go into solutions, and we're going to talk about some acids and bases and other things about solutions. So this is really kind of our last lesson in the math part. And I know stoichiometry is tricky, so if you had some trouble with that, it's understandable, especially in the scenario that we are online. It's hard to even teach it in person, let alone online. But this should be a little bit more manageable. Okay, if you were able to get stoichiometry, you should be very impressed. I mean, it's a complicated process. But when we get into this lesson, should be a little bit more straightforward. Okay, it's not hard math. It is math, but it's not the hard math. Okay. So the lesson is on what we call percent composition in chemistry. So again, quantitative chemistry, so we're going to be taking measurements, we're going to be using numbers and calculations in order to determine something. So basically, the percent composition answers this question. If we have a compound, how much of each element do we have in that specific compound? So I'm going to give you kind of an example here. Okay, so if we have 100 grams of aluminum, well, aluminum's an element. Okay, it's not a compound, it's an element. So if you say you have 100 grams of aluminum, okay, assuming that the purity is high, okay, we can talk about purity a little bit later, but if you have 100 grams of pure aluminum, then you have 100 grams of aluminum. Okay, and that makes sense. It's an element. Okay, because you can't break it down any further. It's not like it can break into smaller pieces. Okay. However, if you have 100 grams of aluminum oxide, now remember aluminum oxide's an ionic compound, it's a rock, okay? And again, so that's where we get our metals from, okay? If you have 100 grams of aluminum oxide, you don't have 100 grams of aluminum. You have 100 grams of aluminum and oxygen, but in this case, most of the weight is actually in the oxygen, okay? So you actually only have about 26 grams of aluminum in this rock. Okay. So how they got this pure aluminum that I'm pointing at over here is they've basically taken this rock and gone through a process called smelting, okay, where you isolate the metal, you pull out all the aluminum. So you would have to use hundreds and hundreds of grams of aluminum oxide in order to get 100 grams of pure aluminum. So what we're going to do in today's lesson is we're going to show you, well, how do you calculate that? How did you know that there was only 26 grams of aluminum if I have 100 grams of aluminum oxide? And that's what today's lesson is about. Now, when would you use this? Well, chemists do a lot of odd jobs. Okay? They work in all kinds of different fields. And one of them, especially if you really like ionic compounds, is in land surveying. So if somebody tries to purchase a property and they want to mine, say, some rock that are in there, so they want to pull out some metals, they go to this mountain or this area and they look at the rocks in there and they say, oh, there's a whole bunch of magnesium oxide, let's harvest magnesium, or there's some nickel ore, or there's some silver ore, or there's all kinds of different metals that they want to harvest. Well, they would go to a chemist in order to determine, well, how much actual metal is in there. Okay, I have a whole bunch of rock, but I want to know how much metal's in there because that's the only part that I can sell. So they would go to a chemist and say, can you do a survey of this land and tell me the value of this land? Tell me how many grams or more it would be in tons. How many tons of metal do I have in this mountain? So chemists use percent composition in order to calculate how much each element in grams or kilograms or tons are in a specific compound. So here's a case scenario. Okay, say somebody's thinking about buying a mountain for say like $120 million. Okay, so they look at it and they say, okay, that contains 190,000 kilograms. I know these numbers are just arbitrary, okay, because these would be very small, but we'll say it contains 190,000 kilograms or 190 million grams of iron oxide ore. So they're going to be after the iron in this case. They don't really care about the oxygen. Oxygen's free, but the iron is what they're going to want to harvest. Okay, and this is kind of what an iron ore is right down here. So this is what iron ore looks like. It's just basically a rock. Okay, any ionic compound, it's going to be a rock or a crystal. So what the company would want to do is they'd want to harvest the metal from the ore and then start selling it. Okay, and you could look up the prices for iron. Again, I just kind of made up these values, but there's a price, the world price for what iron sells for. Okay, and then they would just sell all that iron. So they want to know, is the investment worth it? If I'm going to buy it for $120 million, can I make more money? Is there more metal in there that I can sell so it's worth it? Or am I going to lose money by buying this mountain? Okay, so they'd want to know, well, one, how much iron is in that 190,000 kilograms of the rock? Okay, and then they'd have to know, well, how much can I sell it for? And that's what today's kind of lesson is going to be about. It's kind of calculating these kind of things. And this is just a case scenario of when you would use it. And our lesson or our learning check is going to be revolved around these kind of case scenarios. Okay. So in order to solve these problems, we need to know a few things, okay? And they're things that we've already gone through. One, you need to know the chemical formula for the compound. Okay, so when I say iron 3 oxide, you would have to know that that's the chemical formula. And that's why at the very beginning of this unit, of this course, we really emphasize the idea of understanding chemical formulas, using the crisscross rule, okay, and then making that formula, because that's key, is you have to know the formula. Okay? Now, once you know the formula, the next part is you need to know the molar mass of each element in the compound. And you get that from the periodic table. So a periodic table, it's going to have it, if I kind of have a blown up version of it right here. So if we look at iron, okay, the atomic mass and the molar mass is the exact same thing. Okay, so sometimes the periodic table will label it as atomic mass, but molar mass or atomic mass is the same thing. So what you have to do is you have to look at your formula and say, well, I have 2 irons. So if each iron is 55.85 in this case, I've got 2 of them. I go 2 times 55.85. Right. And I get the weight of iron is 111.70 in that compound. So now I've added up this. So I'm getting the molar mass of the compound, something that you guys did during stoichiometry. Okay. Next, now I have to go and say, okay, well, how much is the oxygen? I've got 3 oxygens. Well, how much does oxygen weigh? Oxygen weighs 16.00 grams per mole. And again, you would get that from the periodic table. You'd have to have a periodic table with you. Or you could just look it up into Google, the molar mass of oxygen. And you find that it's 16. Well, I have 3 of them. So if I have 3 oxygens, that's going to be 48 grams. So now what I need to do is figure out the entire molar mass. Well, what's the mass of this entire molecule here? Let me highlight this, say in blue. So what's the molar mass of this entire molecule? Well, I have to add up what I've just calculated. It's 2 irons and 3 oxygens. So if I add these all together, I get the molar mass is 159.7. Okay? That's the first step that we need to be able to do. Okay? It's just to figure out the molar mass. Now that should be review because you were doing it during stoichiometry. Okay? Now let's go to the next. So this is what we know right now. We know the chemical formula, and we had to start with that. Okay? Because once we knew the chemical formula, then we could determine the molar mass of iron, the molar mass of oxygen in the compound, and then we add them all together and we got the molar mass of the compound. Okay? So the next step is determining, well, what percentage of this total weight, and this is the total weight that we were just talking about right here. Okay, just highlight it again. Okay, that's the total weight. What percentage of the total weight of the ionic compound is coming from iron? Okay? And then what percentage of the total weight is coming from oxygen? Okay. So this is how we're going to calculate that. If I want to know the percentage of iron in the compound, okay, what I basically take is I take the molar mass of just the iron in the compound divided by the molar mass of the entire compound and then multiply that by 100. Okay? So if I'm going to do that out, let me just get my pen here. So the molar mass of iron in this case is 111.70 grams per mole. I'm just going to put that in brackets because it looks a little, even though it doesn't look great anyways. So that's the molar mass of iron divided by the molar mass of the entire compound, 159.7 grams per mole. Oops, again, I apologize for my penmanship. It's very difficult to write on these things. Times 100. Okay. So if we type that in, if I take 111.7 divided by 159.7, I get 70 or 0.7. Then I multiply that by 100, and I get 70%. This is very similar to what you do when you get a test back and you want to figure out your percentage. Okay? You're basically saying, well, what did I get on the test is this number, and what is the test total out of is this number. Okay? And then when you do that in your calculator, you always multiplied it by 100, or sometimes you just converted the decimal to a percentage. So basically in this compound, 70% of the mass is coming from iron. So most of the compound's weight is coming from iron. Now let's do oxygen. Okay, if we're going to do oxygen, we say, okay, what's the molar mass of oxygen? In this case, well, I have 3 of them, and each one's 16, so it's 48. 0 grams per mole divided by the molar mass of the entire compound, let me put bracket 159.7 grams per mole times 100. So if you calculate that out, you get 30%. If you're seeing decimal 3 when you calculate it out, it's because you haven't multiplied by 100. Don't forget to do that. Okay. So 30%. So that makes sense, okay? Because these two should add up to 100%. That when you look at that compound, whenever you have something, most of the weight is coming from iron, and just a small amount is coming from oxygen. Okay. So now we've added to our relation that we have. Okay. Now we know that 70% is coming from iron and 30% is coming from oxygen. Okay. So this means when you have a piece of iron oxide, right, and there's our iron oxide, and you weigh it, 70% of that weight is from iron, and then 30% of that weight is from oxygen. So to give you a simple case, if I had 100 grams, right, of iron 3 oxide, okay, remember the crisscross rule, then that would tell me, because of these percentages, let me highlight this, that means that I would have, 70 grams of iron and 30 grams of oxygen, okay? Because out of that 100 grams, 70% of it, 70% of 100 is 70 grams would be iron and 30 grams would be oxygen. Back to our original case scenario, this is the information that we wanted, this 70% and 30%. That's percent composition. Okay, so now going back to our original case scenario, okay? So now let's figure out, well, if we had this kind of case scenario, is it worth it to buy it? Well, we know that 70% of this ore, okay, of the rock, okay, is iron. So if I take 70% of that weight, or 70% of 190 million grams, I will know how many grams of iron there are in it. Okay, and there happens to be 133 million grams of iron in that mountain. Okay. Well, how many grams of oxygen? Well, I calculate the number of grams of oxygen, and these two things should add up together. Okay. If they don't add up, then we've done something wrong. Now, if rounding, it might be slightly off, but they should be close. Okay, so these should add up to the total weight of the mountain. So basically, if I took all of that rock out of that mountain and smelted it, 57,000 grams of oxygen would be released. Okay? And then 133,000 grams of iron would be left that we could then sell. So now we know how much iron we have, then we can say, okay, if we're selling it for $1.42 per kilogram, I'll convert this grams to kilogram, and then I can figure out, is this investment worth it? Okay, so I think I did just some quick calculations down here. And basically said, you know, if you had 133 million grams and you could sell it for $1.42 per gram, the price of iron, and that's not the price of iron, that would be really, really high price for iron, but we'll just pretend it was, then you would do the calculation and figure out that the mountain, you had $188 million worth of, almost $189 million worth of iron in that mountain. Assuming that you could buy the mountain for $120 million, yes, you should probably buy the mountain. Now that's ignoring operating costs, like the cost to actually extract the rock, but that's the overall idea of percent composition for chemists. So I'm going to go through a case scenario for you, okay? This is the last part of this lesson, because this is what I'm going to ask you to do during the learning check, is to do a few of these. Okay? So here's the idea, is that you have this mountain in Prague in the Czech Republic. It's made of nickel 3 oxide, okay? The mass of the ore is 679 metric tons, okay? So we can just convert that over into grams if you like, or whatever you'd like to use. And the purchase price is $5.6 million. So let's go through what we're going to do in this case. Well, the first thing I need to know, okay, if we go back, is I need to know the formula. What's the formula for nickel 3 oxide? Well, it's going to be Ni2O3. Okay, and again, I just used the crisscross rule. Okay, nickel is 3 plus, oxygen's 2 minus. You do the crisscross. There's my formula. Okay, next thing I need to know is what's the molar mass? Of nickel 2,3 oxide. Right? So I have to look up nickel, multiply that number by 2, then look up oxygen, which is 16, and multiply that by 3. I'm just going to get this for us. If you get into a jam and you figure out the molar mass, you can just type it into Google, like I just did right now, the molar mass of nickel 3 oxide. It's better, though, for you to actually be able to calculate it. I mean, you're going to have to be able to calculate it for chemistry. It's just this might be a way to verify that you're doing it right. So the molar mass of nickel 3 oxide is 165.39 grams per mole. Okay? Remember to include units always when in chemistry. Now I know the molar mass of that. Next thing I need to know now is, well, what is my percent nickel in this case? Now, I'm only going to be selling nickel, so I don't really care about calculating oxygen. Okay? Now, I can, but I don't really care about it, so I'm only going to calculate nickel. So the molar mass of nickel is 58.7. So if I want to get the percent of nickel, I take the molar mass of nickel, which is 58.7 grams per mole, and again, you just get this from the periodic table, divided by the molar mass of the entire compound, 165.39 grams per mole, and then I multiply that by 100. So let me do this for you. So that's 58.7 divided by 165.39. Multiply that by 100. And the molar mass in nickel is 35%. Okay. So, next thing. I basically now know that this weight right here, okay, that 35% of that weight is going to be pure nickel. Okay. So the next thing I need to do now is, and this one's a tricky one, I apologize. I will make sure that there's no conversions. So we're going to have to convert this 679,000 metric tons into grams, because that's what we're selling it for. So I will do that conversion for you, because I'm not going to ask you to do this kind of conversion during your learning check. All right, so we've got, this is going to be a pretty big number. Okay, we're going to just actually change this to pure per metric ton, just because this number is gigantic and we don't want to use it. Okay, so basically we know that 35% of 679,000 metric tons is iron. So what we're going to do is now I need to know the number of metric tons of nickel is going to be 35%. And when we use 35%, we convert it to a decimal. 35% of 679,000. So 0.35 times 679,000 equals 237,700 650 metric tons of nickel. Well, I can sell it for $5.50 a piece. So my last step is then going to be, well, if I can sell each metric ton for $5.50, I've got a whole bunch of them. So I'm going to take 237,650 metric tons multiplied by $5.50 per metric ton. That equals I'm trying to calculate this here, so that is 1,307,000. So total, we got $1,307,075 worth of nickel in there. Okay, so no, it would not be a good idea to purchase this price because it's 5.6 million. Okay, so you may have to go through this a couple times because it is a little bit tricky, but it shouldn't be any kind of math that we're unfamiliar with. It's percent. Okay, and we've been using percent since we were younger, so we may have to do a little bit of review on it, but don't be intimidated by the math in this. Okay, and then email me with any questions.